Hello everyone, this is Dominic, and in this video I will be going over 4 worked examples from section 2.9 to 2.11. This will be covering average versus marginal costs, profit optimization, elasticity of demand, and area optimization using costs. Here are cost functions. As you can see, total cost is equal to C function of X. Average cost is equal to the total cost over X, which also equals the total cost with this dash above. And marginal cost equals C prime function of X. Now I want you to remember these for our upcoming problem. So here's our problem. The cost in dollars to produce Q gift baskets is given by C function of Q equals 160 plus 2Q plus 0.1Q squared. Find the quantity at which the average cost is minimized. Alright, to begin, we first must define when the average cost is a minimum. And as it turns out, the average cost is a minimum when it's equal to the marginal cost. Now, in order to solve this, we first must find the average cost. And as seen in the last slide, it is the total cost divided by X. So then we just plug in our total cost into here to get 160 plus 2Q plus 0.1Q squared divided by Q. Now, in order to better visualize this to solve this part, what we could do is just rewrite this as 160 over Q plus 2Q over Q plus 0.1Q squared over Q. So now we can just cancel out, but well, the Q here stays the same. We just removed an exponent, but basic idea still applies. Cancels out our Q on top and bottom. What we should end up with is 160 over Q plus 2 plus 0.1 Q. And that is our average cost. Now to find marginal cost, we must take the derivative of our total cost. So C prime of X, or Q in this case. No, but anyway, so the derivative of this is equal to 2 plus 0 0.2 Q. Now we can make our marginal cost and our average cost equal to each other, like here. So take our average cost, 160 over Q, plus 2 plus 0.1 Q equals 2 plus 0.2 Q. Now, subtract 2 on both sides, and they should cancel out. Then subtract 0.1 Q on both sides. This should cancel out as well. What you should end up with is 160 over Q equals 0.1 Q. Our second to last step is to multiply both sides by Q to get rid of this division here. And we should get 160 equals 0.1 Q squared. Oh, did I mean our second one? Oh, that was our third step. Sorry. So, uh, our real second to last step, we then divide both sides by 0.1 to get 1,600 equals Q prime. And our final step, take the square root of both sides to get rid of this exponent. And what we should end up with is Q equals 40. And that's the quantity of baskets to produce at an minimum average cost. Now here is our profit functions for our next upcoming problem. So revenue equals quantity of products sold multiplied by the price of the product. Q equals products produced, and profit equals revenue minus costs. So here is our problem. A company sells Q ribbon winders per year at P, or price per ribbon winder. The demand function for ribbon winders is P equals 500 minus 0.2 Q. The ribbon winders cost $20 a piece to produce, plus a fixed cost of $2,000 per year. Find the quantity where the profit is maximized. Now, before we begin, let's label our functions just to for organization later. So our price function, as stated in the problem, is 500 minus 0.2 Q. Our revenue function, now remember from the last slide that revenue is our quantity sold times the price of our products, which is, Q. So this was simplified to 500 Q minus 0.2 Q squared, and our cost function equals 20Q plus 2,000 from our fixed value, from our fixed cost. So now with our functions down, we then plug in our revenue function into our profit function. Excuse me, let me draw a better F there. There we go. Our profit function is just our revenue function minus our cost, which should be eh, eh, 500Q minus 0.2Q squared minus 20Q plus 2,000. To move on, we then take the derivative of our profit function. So the derivative of our profit function, so I have to take the derivative of everything inside here. So this would be 500 minus point, and sorry. So it would be 500 minus plus 0.04 Q minus 20 minus 20. That's it. We then combine like terms, and what we should get is 480 minus 0.04 Q. Then we equal everything to 0 and plus and add 0.4 Q on both sides to get 480 equals 0.04 Q. Then finally, we divide both sides by 0.4, and our answer should equal Q equals 12,000. And that is how many ribbons this company should sell to maximize profit. Now we're moving on to elasticity of demand. Here, our elasticity equals negative P times the demand function prime divided by our demand function. On the right side here is our elastic definitions. If E is less than 1, then it's inelastic, meaning you should increase prices. If E is greater than 1, it's elastic, meaning you should decrease prices. But if E is equal to 1, then it's unitary elastic. So prices should neither increase nor decrease. Another important detail is that whenever you see Q, it is equal to the demand function. So here is our problem. Benson just opened a business selling calculators. The demand function for calculators can be given by Q equals 400 minus 2p squared. Use the elasticity of demand to find the price at which Benson should sell calculators at to maximize revenue. Yeah. So first, we want to take the derivative of Q. So Q prime would equal negative 4p. And since we know that Q is equal to our demand function, we can plug in Q and Q prime into our elasticity function. So E would equal negative P times negative 4p divided by 400 minus 2p squared. And negative p times negative 4p. This would simplify into uh, positive 4p squared. So how do we find the maximum revenue from this? Well, remember our elasticity definitions. If E is less than 1, then we can always increase prices. If E is greater than 1, then we can always decrease prices. But if E is equal to 1, then prices should remain the same, meaning this will be our maximum revenue. So we take our equation here and equal it to 1. Now, so we multiply both sides by the denominator here, which is 400p minus 2p squared. Which should get us 400p squared equals, no, 400, sorry. 4p squared equals 400 minus 2p squared. Next, we add 2p squared on both sides to get us 6p squared equals 400. Then we divide both sides by 6, which would equal p squared equals 400 over 6, which can be rewritten as 200 over 3. And finally, we take the square root on both sides, and our answer is p equals $8.16. And that is the price at which Benson could sell calculators at to maximize revenue. For our final problem, we have area optimization using cost. So, uh, two functions to remember uh, is our constraint function and our object function. A constraint function is equal to a fixed value, say sum equals x plus y. For our object function, it can vary. Example, product equals x times y. For optimization in general, these functions won't be the same, but in our case, we'll be using our example and object functions and examples here. Our final problem here. A farmer wants to fence in a rectangular plot of land adjacent to the northern wall of his barn. No fencing is needed along the barn, and the fencing along the west side of the plot is shared with a neighbor who will split the cost of that side of the fence. If the fencing costs $20 per linear foot to install, and the farmer isn't willing to spend more than $5,000, then what dimensions would enclose the most area? To start, I recommend drawing a picture to visualize the problem. So, a three-sided box with the northern wall being the barn. We'll label east and west with X, and our southern wall with Y. With that done, we can write our constraint function. So 5,000 equals X plus Y. Now each side costs $20 per foot, but the west side of the plot is only $10 because the cost is shared with the neighbor. So our constraint function should look like 5,000 equals 20x plus 10x plus 20y, which can be simplified to 5,000 equals 30x plus 20y. Now, we should isolate one variable, which I'll choose to be y. Uh, So subtract 30x on both sides. Uh, So 5,000 minus 30x equals 20y. Then we divide both sides by 20, and y should equal, oh, 250 minus this 30 over 20x, which simplifies to 3 over 2. We now take our object function, which is area equals x times y. Then we plug in our y, so a should equal x times 250. Sorry, let me draw that better. So x times 250 minus 3 over 2x. And foiling it out should get us a equals 250x minus 3 over 2x squared. Next, we take the derivative of this. So a prime equals 250 minus 3x. Now, equal the whole thing 0. Add 3x on both sides. So we should get, sorry, one moment. So we should get 250 equals 3x. Then divide both sides by 3, which should give us x equals 83.3, repeating, which I'll just write at, 83.33. Finally, to find y, we then plug in our x into our y here. So 250 minus 3 over 2 times 83.33. And this should approximately equal 250 minus 125. And combining like terms, 250 minus 125, which means our y now equals 125. So here are our answers. X equals 83.38, repeating, and Y approximately equals 125. Congratulations! You've made it to the end of my presentation. I hope you enjoyed and learned something new. So goodbye and good luck with your classes.